Hi everyone, my name is Darya, this is Sijun, and we'll be presenting our work Flock, which is a framework for deploying on-demand distributed trust. This is joint work with Pravein from IBM Research and our advisor Raluca. So what is distributed trust and why is it useful? Well, suppose a user Alice has a secret to store on a server. She can do so, but what if that server is malicious or compromised? In this case, the server is a central point of attack. Enter distributed trust. Under the distributed trust paradigm, Alice instead splits her secret into several pieces and distributes them among the servers. Distributing the sensitive data avoids a central point of attack, because even if one server, or up to n-1 servers are compromised, adversaries must now compromise all n servers in order to recover the secret, so Alice's data is still safe. Many distributed trust applications are built on a cryptographic primitive called multi-party computation, or MPC. In MPC, n parties compute some joint function f on their inputs, S1 through Sn. But the core property of MPC is that the parties do not learn anything about each other's inputs other than the final function result. A key example of the benefit of distributed trust is in the application of digital asset custody, in which a user Alice has a wallet application such as Coinbase, as well as a signing key that she uses to authorize transactions and post them to a blockchain. Because these signing keys authorize financial transactions, it begs the question, where can Alice store her transaction signing key? Unfortunately, to date, billions of dollars have already been stolen by compromising these very keys. And that's why many wallet applications have already turned to the distributed trust paradigm, by which the servers first engage in a multi-party computation for signature key generation, which produces the shards of the signing key. Next, Alice takes her transaction and sends a copy to each of the parties, who then engage in another MPC to actually produce the signature on the transaction, which can be posted as usual. Even if one of the parties are compromised, the secret share reveals nothing about the signing key itself, so there's no central point of attack in the system. And there are many other applications. We actually manage a growing community-owned hub of MPC deployments as well. But unfortunately, a large challenge still precludes the mass adoption of distributed trust. And this is that a large class of prior work assumes that n non-colluding trust domains already exist. But this is far from the truth, which gives rise to the deployment dilemma, which is, how can an application provider, which is inherently a single trust domain, go ahead and deploy a multi-trust domain system? So let's give this a shot. As our first attempt, we'll just have the application provider deploy n servers, and then Alice will secret share her data across them. But what happens if the application provider is compromised? Then all n servers are also compromised, and they can collude to reconstruct Alice's secret. So this clearly won't work for our purposes. And it brings us to today's typical model of traditional distributed trust, in which the application provider is tasked with forging n-1 business relationships with other entities that then go ahead and run its MPC workload. Unfortunately, many large-scale institutions have struggled with traditional distributed trust. Whether it's Meta's private advertising, Signal's secret key recovery, Google and Apple's private analytics, or Coinbase's digital asset custody, these institutions have reported that it is difficult to convince other MPC parties to deploy, run, and maintain your application's workload. So imagine how hard this is for your everyday application developer. So our goal in this work was to enable anyone to automatically deploy distributed trust, even just a single application developer. So our key insight in this work is to completely reframe how we think about distributed trust deployment. So in the traditional model, it's the application provider's job to find these parties and deploy the code. We propose the following alternative. Yes, the application provider can deploy one party, but the user Alice is the trusted owner of her own sensitive data, and so she can actually help conduct the deployment for the other n-1 parties. And this results in an automatic deployment paradigm that we call on-demand distributed trust. Our system Flock is for deploying on-demand distributed trust through user-driven deployment by leveraging cloud providers as trust domains. So first, we will show how to reverse the approach to deploying distributed trust by migrating the onus of deployment from the application provider to the user. And second, we design a practical end-to-end system to realize this vision in a way that's both cost-efficient and secure. We also port over 8 different distributed trust applications that span 5 fundamental cryptographic modules.
All right. Before we dive into our system architecture, let us first take a look at our threat model to see who we can trust and who we cannot. So we leverage multiple cloud providers as different trust domains, so we assume that at least one cloud provider server is uncompromised. In addition, our system guarantees malicious security as long as the app that the application provider is building is maliciously secure. Additionally, we assume that the code from the application provider is trusted, and this can be enforced by having the code open source and letting the community scrutinize it. Another great feature of our threat model is that compromised clients cannot affect uncompromised client, and we get isolation between different clients. So now how does this all work? Well, the application provider can just host a server as usual, but now the key insight here is that Alice, the user, can now deploy 2 VMs on 2 different cloud providers. And we can leverage these 2 different cloud providers as 2 different trust domains since they are disjoint entities controlling different set of resources. And now these 3 parties can form 3 trust domains, and they can perform MPC executions together for the distributed trust applications. However, this might work for only 1 Alice, 2 Alice, 3 Alice, or even maybe 7 Alices. However, what if we have tens of millions of Alices, which is the monthly active users for an application provider such as Coinbase has? Clearly, this approach wouldn't scale since we won't be able to amortize the cost of these 3 servers. And so this 1 VM per user per cloud approach will be too expensive and impractical for the ephemeral workloads we strive to support. Our solution is to leverage serverless computing. Serverless computing is stateless compute that exclusively incurs costs at execution. And major cloud providers such as AWS and Google Cloud provides major serverless offerings. Serverless works great for Flock for 2 main reasons. First, serverless incurs no cost when the user is not performing any operations, which means serverless will be very fast. And then second, serverless containers are executed on demand with very low startup time. That means we are able to get very fast services. So now with serverless computing, how does Flock all work? Well, the application provider can just host a server as usual. But now the key idea here is that Alice can programmatically deploy 2 serverless instances on 2 different cloud providers. And these 3 instances can form different trust domains, and they can perform MPC executions together for the distributed trust applications. To put it more concretely, Alice can leverage maybe AWS Lambda and Google Cloud Run as the serverless cloud providers. And then the application provider can host a server on Azure. And these 3 trust domains can indeed perform MPC as needed. Well, introducing serverless is great, but it raises another question about serverless communication. Because for many MPC protocols that we need, it requires communication between these serverless functions in a secure way. And this is typically realized in a secure TLS connection. However, we're unable to form secure TLS connections between the serverless functions because the serverless functions operates behind network address translation, which blocks them from accepting any incoming connections. So the question here is, how can we securely establish a P2P serverless connection? Our main insight here is that we can leverage the application provider as an untrusted relay. Remember that in our threat model, the application provider is untrusted for security, but we can trust them for availability. That means they can host a service for us. So the key idea here is that we can leverage this application provider to host an untrusted relay for us that somehow can securely route messages between these serverless functions. And to realize that, we design a specialized relay protocol in Flock that enables us to establish end-to-end secure TLS connection over 2 consecutive TCP sockets connected to this untrusted relay from the serverless functions. And for more details of our serverless relay, please refer to our paper.
The second main technical challenge that we have to solve in our system is with authentication. As you can see, our system architecture on the right here is far more complex than a standard application. The key issue is that user-driven distributed trust introduces new attack vectors all over the stack. The question is, how can an application provider secure a deployment it just doesn't control? So let's start by identifying these attack vectors. Notice that an adversary could attack at the application layer as in a standard application, but it could also attack the cloud layer or any one of our more complex network connections between the different moving parts of the system. So our task was to design a comprehensive authentication protocol spanning these layers. To secure the application layer, we use MPC Auth, which is a cryptographic protocol that allows a user to authenticate to end parties with the work of just one authentication. So we do the authentication phase in MPC as well. To secure the cloud layer, we use access keys. So clients locally store IAM access keys, and they use these to authorize their invocations. And finally, at the network layer, we use certificates in our relay protocol. So parties will authenticate to one another using previously user-signed certificates. So how do all of these moving parts come together in our running example of digital asset custody? Recall that we have a user, Alice. She has a wallet application such as Coinbase, and she wants to sign transactions and post them. So how can we do this with Flock? Well, first, the application provider has to get the open source code to the client device. Next, Alice's client is going to programmatically deploy the N-1 serverless instances in distinct clouds, and this is all abstracted away from the user. Next, the user is going to split a pin that we'll later use for MPC Auth and split it among the parties. The parties are going to engage in an MPC for signature key generation over their secure network connections. And now, Alice is going to be ready to authenticate and get her transaction signed. So she has a pin attempt, which should be equal to the original pin. She's going to split it, distribute it among the parties, and now they're going to form their secure network connections again. And this time in MPC, they're going to do MPC Auth to check whether the pin attempt is equivalent to the original pin. And if it is the case that this MPC check passes, Alice is now authorized. So what she's going to do is take her transaction and send a copy of it to each of the parties. Next, they're going to establish their secure network connections again, and they're going to perform another MPC for signature generation. And finally, we have a signature on the transaction.
To evaluate Flock, we implemented 5 different cryptographic modules, which are signature generation, decryption, secret recovery, PIR, and data freshness. And these 5 cryptographic modules serves as a core foundation of the 8 applications that we support. And we implement these 5 cryptographic modules as well as Flock's framework in roughly 2,000 lines of Go, 2,000 lines of Python, and 2,000 lines of C++. And for evaluation, the main question we're trying to ask is Flock's performance comparable to traditional distributed trust? And to investigate that, we consider 2 different setups. The first baseline setup mimics a traditional distributed trust use case where the application provider will host 3 servers on 3 different clouds: AWS, GCP, and Azure. And for Flock, we'll have the application provider host a VM on Azure, and then the user Alice can deploy 2 serverless instances on AWS and GCP. So now let's see the latency and throughput comparison between Flock and baseline. The figure on the left shows the latency for the decryption module, which is one of the cryptographic modules that we supported. And the x-axis here shows the difference in file size, which is the input size to the function, and the y-axis here shows the difference in latency. As we can see that as the file size increases, both Flock and baseline has an increase in latency, which is expected. But then if we compare Flock and baseline's latency across all different file sizes, you can see they're super comparable. And across all the other four applications, we get a similar conclusion. That is, Flock only has minimal latency overhead compared to baseline. For throughput, we see a similar story here. So the figure on the right shows the normalized throughput for all the 5 cryptographic modules that we support. And the x-axis here shows the different cryptographic modules, and the y-axis here shows the request per minute ratio between Flock and baseline. As we can see that Flock indeed has a very similar throughput compared to baseline, and it's able to achieve at least 95% of the original throughput. Finally, let's go over to cost comparison. Well, cost comparison is a bit tricky here because VMs and serverless operates under different cost models. So VM has a fixed hourly cost, whereas serverless cost is per request. So to calculate cost, we have to first convert the server's fixed VN cost to per request cost by estimating it based on each module's maximum throughput. And this table at the bottom shows the cost comparison for the two cryptographic modules that we support, signing and decryption. And first, we want to note that the networking costs between both Flock and Baseline are the same, so the main difference comes from the difference in compute cost. So for signing, this is a relatively networking light protocol and compute light protocol, and the bottleneck in cost comes from compute. And overall, Flock has a roughly 2.5x overhead per request. For decryption, this is a more compute-intensive and network-heavy protocol, and networking cost becomes the major bottleneck. And overall, Flock only has a 1.3x overhead. And we would like to note that despite all this overhead, Flock's system cost is still negligible compared to the cost of actually setting up business relationship in a traditional distributed trust setting.
So zooming out to a bird's eye view of Flock, we combine the security guardrails of each of these clouds and reverse deployment to leverage users at the core of the system. And so in this way, Flock is the first way for an application provider to automatically and immediately deploy distributed trust. Here is our code as well as our paper, and we're happy to take any questions you might have.